Hey everyone, this is the Radical Tutor here explaining, and in this video we are going to look at the state and the proof of Green's theorem. So we are going to see how the Green theorem states and how we can prove the Green's theorem. Alright, so how do we state? So we are going to start by stating it. Alright, so to state the Green theorem, you say it states that if P and Q are two functions having continuous first order partial derivatives with respect to x and y in the region E bounded by a closed curve C, then the closed curve integral of p dx plus q dy is equal to the partial derivative of q with respect to x minus partial derivative of p with respect to y in the order dx dy. So what we are saying is that under Green's theorem, you will always be given the functions p and q. So you will be given two functions, and having given the two functions, we are saying that we can differentiate the two functions with respect to x and with respect to y, and there should be under any closed curve, which in this case it can be C. So if you are able to differentiate q and p with respect to x and y under a given closed curve, then this condition here must be satisfied. So what we are trying to do is now to prove that this is equal to this. So what we've done here is the stating. Now we want to see how we can prove it. Okay, so when we say that functions p and q are continuous, meaning that they exist and their partial derivatives can surely be found. That's the meaning of continuous. Now, mainly what happens is that if you are given this part is sometimes called the line integral, and this side which is here is the Greens that now we are doing. So what I'm going to do is I'm going to show that the right hand side is equal to the left hand side. So I'm going to prove from this side, taking it to this side, and see if for sure this can be found. Alright, so this is how to state Green's theorem. So let's dive into the proving and see how we can prove the Green's theorem. Alright, so for you to prove Green's theorem, what you're going to do is I'm going to draw a diagram where I'm going to illustrate how the Green theorem operates. So allow me to draw the diagram here. So I'm going to draw this diagram. So I have this and this. Remember, this is the x-axis and this is the y-axis, and then I'm going to draw an ellipse from this diagram. So I'm going to draw an ellipse. So I'm going to draw it like this, like that. So that's an ellipse that I've drawn. Now for Green theorem, what we are trying to look at is that we are trying to look at a particle which can move from one point to the other, hovering around this conic section that I've drawn. Okay, so now when we are looking at Green theorem, we are looking at a particle that can move from point A to point B to point C to point D, or I can say point A to point P to point B to point Q, like that. So if we are able to have a particle which is moving from point A to point B, P, B, Q, and then back to A, then you can easily get its integral. So you can integrate that particle which is moving, or which is moving from this initial point, going to all the points and coming back to the initial point, like that. So under Green theorem, we are actually integrating a certain function through the points at which the particle is passing at. Okay, so now what we are going to do is that for you to integrate a function, for you to integrate any given function for this particle which is moving from one point to the other, what you need to do is to first have limits. Remember, for you to integrate something, meaning that you're supposed to have limits. Now, how do we get the limits? So the limits are going to be gotten in terms of the x-axis and in terms of the y-axis. In other words, we are going to get the limits in terms of dx, dy, and dy dx. Okay, so when you are going to get the limits, consider the points which are lying on the x-axis and the points which are lying on the y-axis. So if you are able to see properly here, you are going to find that A and B are on the x-axis, and also P and Y are lying on the y-axis, like that. So when getting the limits, we are going to say we are going to create limits for A and B, as well as creating the limits for P and Q. So let's create the limits and see. So what we can do is I can say here we can create the limits from that point to be A for x-axis, and also going to B, we can put that as B. So we are assuming that if a particle is moving from A to B, meaning that it is moving in the horizontal direction, and the limits that we are taking are for x. So meaning that the point to move from point A to point B, like that. So those are the limits for the A and B, or for a particle which is moving from point A to point B. Then now we are also going to say that if a particle is moving from point P to point Q, meaning that it is moving in the vertical direction, because it is moving from here going to there, so it is being oriented in the y-axis, like that. So if it is being oriented in the y-axis, then we are going to say that it is moving from this point that we can call as C, which you can call as C, to this point that we can call as D, like that. So meaning that those will be the points or the limits for the y-axis, which is C to D, and the points or the limits for the x-axis are from A to B. Now, having said that, we should also assign other limits for all the points that are going to be separated from the A, B, C, and D limits that we've created. So in this case, we can say let us also have the limits of x. Remember, we are saying that point A and point B are giving us the limits of x-axis, or the x. So what we are going to do is we can say that let the limit here to be x is equal to g1 of x, and the other limit of b, which is going to give us x is equal to g2 of x, like that. So we've created other new limits for A and B. Then let's also create other new limits for P and Q, which in this case are going to act as the limits for the y-axis, or the limits of y. Okay, so we can say let P have the limits. So let P have the limits y is equal to f1 of x, and Q have the limits y is equal to f2 of x, like that. So we now have those limits given to us. Now, from there, that's when now we can be able to prove the Green's theorem. So if you're able to just come up with this diagram, then Green's theorem becomes very easy for you to prove. So now, when proving the Green theorem, you are trying to look at how you can complete the revolution by moving from one point to the other back to the initial point. So what we are going to do is that we can say, if we are integrating the area, okay, if you're integrating the area of this moving point from A to B, so let's say if a point is moving from A to B, meaning that you are moving from this point going to B, from point A to point B. So we can say we are integrating that particle which is moving from point A to point B over a given function, which is a function of x, y, and we can take the order of integration to be dy dx, like that. So we are taking the order of integrating a particle from A to B with respect to y and x, like that, in that order. Now if we have dy dx, meaning that we are taking the first limits here to be for y and the other limits here are for x. Now how do we get the limits if a particle is moving from A to B? Because this is the route that we are taking there. So if you are moving from A to B and we want to get the limits of x first here, meaning that what will be the limits of x? I think you're able to see the limits. We are moving from point A, the limits of x there is what? A. To point B there, what will be the limits of x? It's B there. So we are moving from this point where the limits is A to that point where the limits is B. So we are moving like that. Okay, so we are going to say our limits there will be A to B. Now we've gotten the limits of x. So we've gotten the limits of x here, which is this. Now we need to also get the limits of y, which is this. Alright, how do we get the limits of y? So remember, we are saying that we are moving from this point to that point there. So if x is A and x there is B, what could be the limits of y from point A to point B? So getting the limits of y, what we are going to do is to say y is moving from this point to that point. Now, when getting the limits of y, you need to complete the revolution. So completing the revolution, meaning that here, remember, we've gotten the limits of x from point A to point B. Now, completing the revolution, we can also say that the particle can also move from P to what? To Q. So if you're moving from here to here, and then you also move from here to here, that means you've completed the revolution. So getting the limits of x, we've moved from here to here for the particle, and then for us to get the limits of y, because the limits of y can only be gotten from p and the q, so meaning that we are going to move from p to q like that. So which limits of y are from p to q? So the limits of y from p to q are y is equal to f1 of x to y is equal to f2 of x. So we are going to write y is equal to f1 of x to y is equal to f2 of x. Okay, so this is the first route that we can take. So we've taken the route where we are moving from point A to B and also from point P to Q, where we've gotten these limits here. Okay, now from there we can also take another choice of integration. Remember here we've gotten the choice of integration to be dy dx. Now we can also take another choice of integration which can be dx dy. So taking that choice of integration, what you are going to do is you are going to say that, let's say that our choice of integration is going to be integrating this function x comma y with respect to x and then later on with respect to y. That means we are first getting the limits of x, then we get the limits of y. So getting the limits of x, meaning that these will be the limits of x and these will be the limits of y here. Okay, so we are going to start by getting the limits of y, then we get the limits of x like this. Now, how do we get the limits of y? So to get the limits of y, you are moving from point P, the particle is moving from P to what? To Q, because we are saying that you can only get the limits of y if a particle is moving from P to Q like that. So what is the limit of P here, where the particle is starting? The limits of P there is C. And where the particle is going, what's the limit of Q? Of Q there, the limit in terms of y is D. So we are going to say that the particle is moving from C to D. Okay, those are the limits of y. Okay, from here to there, the limits are C and D for y. Now we need to get also the limits of x which are here. So to get the limits of x which are here, we can only move from, for you to get the limits of x, you need to move from A to B, because A and B are the only numbers or only variables rather that are on the x-axis. So we are moving from this point to that point. So at this point, what's the limit of x? The limit of x is g1 of x to g2 of x. So we are going to put here, we put g1 of x to g2 of x like that. So these are the two choices of integration that one can take if you are trying to look at the area that the particle is taking, if it is to move from A to B and then P to Q. So that's the first that is how you can get these two choice of integrations. All right, now having made these assumptions, what we are going to do is we are going back to our state. Remember, this is the statement that we want to satisfy. So we want to prove that this is equal to this. Now remember, I'm saying that I'm proving from the right hand side, proving that it is equal to the left hand side like this. So if you are proving that the right hand side is equal to the left hand side, I'm going to pick this as my equation. So I'm picking that as my equation, which is the double integral of sigma q over sigma x minus sigma p over sigma y. So I'm going to pick it here, which is going to be, okay, so I'm going to pick it as the double integral of sigma q over sigma x minus sigma p over sigma y. Okay, and this is given as dx dy. Okay, so this is what we have. Now we want to prove that this which we've written is supposed to be equal to this one here. So this is equal to that. Now how can we prove? We are just going to replace. Remember, we've made some assumptions here that we've made that a particle can move in this direction or it can also move in that direction, having these limits here. So if we have these limits, what we can do is, first of all, we are going to multiply the integrals here. So we have the double integral, we multiply it with what is inside. So we multiply this with that, we also multiply this with this. So multiplying this with that, you are going to have the double integral. So you are going to have the double integral of sigma q over sigma x minus, we multiply also the double integral to the sigma p over sigma y. We are going to have also the double integral the double integral of sigma p over sigma y, like that, and then we put the x dy. So we're going to put the x dy. So we can put the x dy here. So if you want, you can put the x dy here. You also put the x dy here, because also this dx, why have I distributed to this one and this one? It's because this dx dy is outside, meaning that it is affecting both the function of q and the function of p. All right, now from here, what we are going to do is we are going to replace. So we are going to replace. How are we going to replace? We are going to replace that. Remember, this is the function of q and this is the function of y. Okay, this is the function of p and this is the function of y. Now, in correspondence with the with the assumption that we made. So the assumptions that we made here are this one and this one here. So we can term these two functions as this to be our p and this to be our q according to alphabetical order. So we can term this, the first function on top there, in the assumption to be p and the other one to be q. So having these two functions, what we can do is we can now replace them in where? So these assumptions that we made here, we are going to replace them in this statement that we've made here. So we are going to replace these two functions in this statement. Now, how can we replace them? We are going to replace them in such a manner that, remember, we have sigma q over sigma x dx dy. So the function of q here is going to be integrated. Remember, this is the function of q. So the function of q, if we are saying that this is the function of q, meaning that the function of q is going to be integrated along which limits? Along these limits here. And this function of p is going to be integrated along which limit? Along these limits. But don't forget the order of their integration, that the function of q is integrated with respect to dx dy and the function of p is integrated with respect to dy dx. So that's what you are going to do. So you are going to replace. You are going to say this is the double integral of sigma q over sigma x dx dy. Now, you are going to do this. Before I even write the dx dy, you need to check what you have here. What is q being integrated with respect to according to the assumption? It is with respect to the x dy. So we are going to put the x dy here. So we are going to put the x dy. And then now the limits of q in the assumption, the limits of q in the assumptions are that we are integrating from c to d. So we put c to d and g1 of x to g2 of x. So we put g1 of x to g2 of x, like that. Those are the limits of the function q. And then we have the minus here. So this is our minus. Then also we put the limits of the function p, which is sigma p over sigma y. And according to the assumptions that we made, we've seen that p is integrated in the order of dy dx. So here, instead of us putting this dx dy, we now put dy dx, because this is what we have in the assumption, that the function of p should be integrated in that order. So by doing so, we are going to put dy dx. But please don't forget to put the limits of the function p. So the limits of the function p, according to the assumptions that we've made, are that we are integrating p with respect to a, b, and f1 x to f2x. So we're going to put here a to b. So we put a to b, and then f1 of x to f2 of x, like that. So that's what you have. Now, after you've written those two limits for both the function p and the function of q, what you are then going to do is to integrate, because you now have your function q with its limits. You also have the function p with its limit. So what is just remaining there is to integrate. Here you are integrating with respect to the x dy. Here you are integrating with respect to p with respect to y. Okay, in that order. So here let's integrate. Integrating here, first we integrate with respect to x, meaning that we keep the first limits constant. So keeping the first limits constant, integrate with respect to x. We are going to say, so we are going to keep the first limits for c to d constant, and then when you're integrating, meaning that you are opening the bracket, integrating sigma q over sigma x. Remember, when you integrate a differential, you go back to the original function q. So you go back to the original function q of x comma y. Okay, and then you put the limits. So you put the limits from, remember we've integrated with respect to x, and the limits of x are g1 of x to g2 of x. So you need to put the limits here on down is g1 of x to g2 of x, because we integrated with respect to x, so we need to put the limits up and down. Okay, and then since we've integrated with respect to x, meaning that the dy remains the same, so the dy here remains the same like this. Okay, we've integrated with respect to x and the dy will remain the same, minus we also keep the limits of a to b, which are these, and then now we integrate with respect to y on the function p. So integrating with respect to y, since it's a sigma p over sigma y, it means we are going to remain with the function of p of x comma y. Okay, and then after integrating with respect to y, we are going to put the limits, which are f1 of x to f2 of x. So we put f1 of x to f2 of x like that, and then the x remains, which dx, this dx which is here, so that dx remains. Then after that dx has remained, what you are going to do is now to replace your limits. So you are going to replace your limits. Remember, we are replacing these limits on what here we integrated with respect to x, meaning that we are only replacing them on x, and also these limits we integrated with respect to y, so we are only replacing them on y. So let's do that. So to do that, what you're going to do is to say we have the integral of c to d, and then we replace, this is going to be q of, where there is x here, we put the upper limit first, which is g2 of x comma y. So we've replaced the upper limit, then minus. Okay, so you say minus, you also put the lower limit. So the lower limit is going to be q of open. We also put the lower limit, which is g1 of x. Okay, like this. I don't know if you've seen what I've done. What I've done here is simply to replace the lower limit and the upper limit. Remember, when you're replacing the limits, meaning that we're creating two brackets. Where there is x, you put the upper limit, minus where there is x, again you put the lower limit, which I've done here. So you can just do this. Let me just show you here. I have replaced like this, g1 of x and then comma y, because we are only replacing on x, keeping y the way it is. So I've replaced on x the upper limit and the lower limit, which we've done here. Then the dy is still attached there. This dy here, you still bring it like that. Minus, you come here, you keep the integral from a to b, and then here we've already integrated with respect to y. So we need to put the limits, this upper limit and lower limit, where there is y here. So we are going to put the upper limit and lower limit where there is y. So by doing so, we are going to say our upper limit, okay, let me do this. So our upper limit, let me start from here. So we say we have q, we are replacing our upper limit. So our upper limit is, okay, let me just erase this one. So we have this p here, and we are replacing our upper limit where there is y, okay, which is f2 of x. So we say f2 of x comma y. Sorry, let me do this. Let me remove this one and say p. So where there is y, that's where we are replacing. So where there is y here, that's where we are replacing with f2 of x, and the x remains the same. So the x remains the same, comma, where there is y, we are putting our upper limit there, which is f2 of x. Okay, then minus, again the same function p, open x, comma, where there is y, again we put the lower limit, which is f1 of x. So we put f1 of x like that. Now after putting the f1 of x, we can even do this. Or let me use another color. We can do this, you can do that. Okay, don't forget that at the end there is the x here. At the end there is the x. At the end of it, or here there is the x. So now from here, what we are going to do is we are going to distribute the negative throughout what is inside here. So we're going to distribute this negative throughout what is inside. So let's do that. So to do that, you are going to say, we start by writing this one here. So we'll write it the way it is, and then we first to distribute the negative to this function to also that function there. So let's do that. So to do that, we are going to have the integral from c to d of the function q of g2 of x comma y minus the function q again, which is this function here, of g1 of x comma y dy minus, okay, so we are now distribute the negative to this, which is going to be the integral. So we are going to have the integral. So of course what you can do is that if you are distributing the negative, remember you have this negative times integral from a to b, which is going to be the integral from a to b, and then you write this function, which is p of x comma f2 of x, okay, and then minus. So there is a minus here, which is this minus the function p again. So you multiply this negative, you are multiplying this negative times this negative, you get a positive. So this negative and this negative, you get a positive, which is going to give you a plus. So this is going to give you now a plus. So plus this function here, which is p of x comma f1 of x, like that. All right, and then at the far end we have what? We have the x. That's what you have. Okay. Now, what you're going to do is, you know that this function here is the whole of this function is being multiplied by dy, and the whole of this function is being multiplied with a dy, and the whole of this function is being multiplied by the x at the far end there. That means we can distribute the dy. So we can distribute the dy to this. We can also distribute it to this one. We can also distribute the x to this function and to this function. So by doing so, we are going to do this. We are going to say, we distribute now. So we are going to have the integral from c to d, which is this one, of the function q of g1 of x comma y minus the function q of g1, or of course you can put the dy, because that's what we are distributing. We are distributing this dy to this and to that. So we can put dy here. So we're going to put dy minus the q. We also distribute the dy to this. We are going to have q of g1 of x comma y dy. Okay, minus, we also do the same, minus, we distribute the dx to this function and that function, so which is going to be the integral from a to b of p of x comma f2 of x, which is this one. I don't know if you're able to see it. Then plus the integral of this function, which is also the x comma f1 of x dx. So here you put the dx here, you also put the dx here, like that. Okay, that's what you've obtained. Now after you've obtained this, what you're going to do is, remember, you are integrating the whole lot of this function from here to here, having these limits here. So you're integrating the function from here to here with respect to c and d, meaning that if you want, you can even say this one also is integrated from c to d. Okay, also here the same, if this is integrated from a to b, meaning that even here also integrating this one from a to b. Okay, now that's what you have. So after you've done that, what you are going to do is, we are going to change the order of integration. So if you change the choice of integration, remember here you are integrating from c to d, and here you are integrating from a to b. So if we don't want to remain with the negatives here, we need to change the choice of integration. So what happens is that if let's say you are if you have a point, let's say you have this region here, and this is point A, this is point B. So if your choice of integration is like this, if this is 2 and this is 4, so if you are moving in that direction, meaning that you are saying you are moving from the limits 4 to 2. So that's those will be your limits. Now if you decide to change the direction, let's say you are moving from, instead of you moving from B to A in that direction, which is the anti-clockwise, and then you decide to move the clockwise direction, meaning that the limits will change to have a negative in front. So that's what happens. So even here, this is the concept that you are going to use. So I don't want to remain with the negatives here. I don't want to remain with these negatives. So for me to remove the negatives, I'm going to change the limits. Instead of me integrating from C to D, I'll integrate from D to C, so that the negative changes to positive. Even here, instead of me integrating from A to B, I will integrate from B to A, so that the negative there changes to a positive. So that's what I'm going to do. So by doing so, I'm going to write my final answer. So I'm going to have the integral from C. Okay, let me do this again. So we are going to integrate from C to D of the function q of g1 of x, g comma, let me do this. We are writing this. I don't know if you're able to see it. We are writing this one here. So we are going to write it as q of g comma x1, x1, or g1 of x. In other words, so we are saying this is g1 of x. So we write the g1 of x, comma y dy. I've written this one here. Then I'm changing the choice of integration from C to D. Then I'll write the limits as D to C. So once I change these limits here, instead of C to D, I write D to C, meaning that this negative here will change to a positive. So this is going to change to a positive, and then you remain with this, which is the G1 of x, G1 of x1, comma y, like that. Okay, so I've written for this one. Then I'll go to this one again. I need to change this negative to a positive. How can I change the negative to a positive? I'm going to change the limits. Instead of me writing A to B, I'll write B to A, like that, so that this negative changes to a positive. All right, so now we are going to change this negative to a positive, and then say we are now integrating from B to A instead of A to B, of which function of P of x, comma f2 of x. Then this one is going to be dx plus the integral from, this one is already a positive, so it is going to remain the way it is, which is A to B of x, comma f f1 of x dx, like that. So here you have dy. Okay, so here you have dy. Here, let me write here this one. For this one you have dy, and this one you have dx, like that. Okay, now after I've written those things, what you can do is that you can say integrating, this is, as you can see, you have, this is the function of dy, and this is also a function of dy. This is the function of dx, this is also a function of dx. But don't forget that the function of dy, here you have a q, there also you have a q. Don't forget, because that is what we've been writing. So we have a q and a q, then here also you have a p, and there also you have a p, like that. So don't forget that this is pp, that is qq, like that. So even here you have qq, pp, like that. So now what we are going to do is that, since this is the function of q and this is the function of q, what we are going to do then is to put them in one format. So how can we put them in one format? We know that this is a function of q integrating from C to D, and this is a function of q integrating from D to C. So if we have that, we are saying that we are actually integrating these under one closed curve, which is, instead of us writing from here to here, because this is the same function of q integrating from C to D and D to C, meaning that we are moving around a circle, like that. So instead of us writing this to that, we just write it as one limit, which is a closed curve of a given curve C, of what? Of a function q of g1 of x, y. Here also we have g1 of x, 1. Okay, g1 of x 1 and g1 of x. All right, so I've seen that we missed something here. We missed something here instead of this one here. Remember, this is g2, so this is supposed to be g2, meaning that this one also is not supposed to be g1 but g2. Here also g2, so you need to rewrite those. So this is g2 like that. Okay, then from there now we are saying that you can rewrite this. So you can write this function from here to here. It is integrated from a closed curve from C to D, D to C. So in other words, you have this, and then you have C to D like this. So if you are moving from C to D and then D to C, meaning that we are moving around this circle like that. So it's a complete revolution or complete circle. So what we can do now is to just write them under the same limit. So we can just say we are integrating along now a closed curve C of the function of Q, a function of Q dy, because this is under dy, this is dy, this is also dy. So we just write that we're integrating the function of Q of x comma y of x comma y. So instead of us writing the g2 of x comma y, we just write this is x, that is y. So you just represent them as x comma y. Even here also this is x comma y, so you presented them as x comma y of dy. So I've written this and this in one expression, which is this, and then we go to plus. So we go to this plus, so you write the plus there. So you say plus also the integral of a closed curve C of this function and this function also are being integrated on the same limits, which is dx, and this is p, that is p, integrating from b to a and a to b, meaning that we are integrating along a closed circle or curve, which is like this. So we can say this is a, that is b. So we're moving from a to b and then b to a like that. So meaning that we are integrating along a closed curve or circle. So now that can be represented by the integral of a closed curve C of, you only pick the p, the function p, so you only pick the function p of x comma y. So you pick the function p of x comma y. So this is p of x comma y, and then you write the dx like that. Okay, so this also can be written as the integral. Since this is under the closed curve C, this is also under the closed curve C, meaning that we can factorize the integral, which is common. So the integral of a closed curve C is common. Here you are going to remain with Q integrating functions x and y with respect to y, which can just be written as Q dy plus this one as p dx like that. Now if you want, you know that addition is commutative, meaning you can write this as the integral of a closed curve of C. You start with the p, which is p dx plus q dy. So I've just swapped them because we know that addition is commutative. So this is what we've obtained like this. So if you are to check, this means that we've proved the Green theorem that the integral of p dx plus q dy is equal to this. So we are proving that this is equal to this, and for sure this is what we've obtained here. So this is what we've obtained here, and then therefore we say hence proved. So that's what you do when proving the Green theorem. So it is as simple as that. See you in the next video, but please don't forget to subscribe to my YouTube channel. Don't forget to click the subscribe button to receive more videos whenever I make such interesting videos.